All right, so today we're going to talk about Chapter 13, Day 4 Notes, which focuses on rational and irrational roots. So as a reminder, a rational number can be written as a over b. That might reduce to a whole number, a fraction, decimal, a repeating decimal, a truncated decimal. But an irrational number would be something like square root of 2, square root of 10, or pi. All right, so we're going to focus on rational roots mainly, and Q is considered to be the factors of the leading coefficient in an equation. If you write the terms in descending order, then this would be the first coefficient that you see. And then the P would be considered to be the factors of the constant, which again, if you wrote it in descending order, the P would be the last value in the equation. You're going to make a list to start that includes all possible rational roots. Not all rational roots, but just the ones that are feasible. And you're going to make that list from plus or minus P over Q. All right, the upper bound theorem and the lower bound theorem we're going to come back to when we have an example to fill in. But for now, we're going to look at the location theorem. So the location theorem says, let f of x be a polynomial, all of whose coefficients are real numbers. So you can have some term like 2x. You can't have 2ix. That would be an unreal number. If a and b are real numbers such that f of a and f of b have opposite signs, like one is positive and one is negative, then f of x equals 0 has at least one real root between a and b. The easiest way to think about this is graphically. So if you look at this graph down here, if I were to determine where the graph changes from having negative values to positive values, right? If I were to select any a value, let's say here's a, this is a negative number as an output, and then here's b, this has a positive number as an output. I know that there needs to be at least one real root, otherwise known as an x-intercept, somewhere between a and b, which, as you can see, there is one. It has to, in order to go from the negative side to the positive side, it has to cross over the x-axis somewhere, and the x-axis is where you would find your root. All right, so more generically, if we have any polynomial, let's say that this is a portion of that polynomial, and there are 2 points. This point is a comma f of a, right, like x and y, and this point is b comma f of b. Oops. F of b. And I know that f of a is negative because it's below the x-axis, and f of b is positive because it's above the x-axis. Then I know that there has to be at least one real root somewhere between a and b. So I'm going to call this a root between a and b. All right, so let's take a look at an example. We have f of x equals x to the fifth minus 3x squared plus 4x plus 2. If we were to do f of negative 3, take negative 3, substitute it everywhere you see an x. Right? If we did negative 3 to the fifth minus 3 times negative 3 squared plus 4 times negative 3 plus 2. If you do that, you can do it in your calculator if you'd like, you get negative 280. If we find f of negative 2, you get negative 50. F of negative 1, you get negative 6. F of 0, you get 2. F of 1, you get 4. And F of 2, you get 30. Well, let's take a look at our outputs. So we have a negative, a negative, a negative, a positive, and a positive. So because I noticed that there's a sign change here between the negative and the positive value, I know that there has to be at least one real root somewhere between negative 1 and 0. And if you go and look at the graph, that's what shows this. So there is a root somewhere between negative 1 and 0. We'll talk about later how to actually find that. But for now, you can at least identify that. All right, so let's go back to this upper bound and lower bound theorem. All right, so let's use the equation from below. We're going to use this equation. All right, and we're going to test to see, well, what would be my potential upper boundary and lower boundary. So my equation, I'm just going to rewrite it, is f of x equals x to the fifth minus 3x squared plus 4x plus 2. All right, so I know that my p's and q's for this one, I could find all the factors of my constant, which is 2. So I would do factors of 2 are 1 and 2. And I would look at the factors of the lead coefficient, which is 1. So factors of 1 is 1. And that means that I could either have positive or negative 1, 1 over 1, or positive or negative 2. So I'm going to test for my possible root. If I were just to test the number 2, I'm going to do my synthetic division. Make sure that you indicate a 0 where you are missing some terms. And if I do my synthetic division really quickly here, I'm going to look at, well, what do I have in this bottom row? So if the third line in this synthetic division has no negative numbers, right? This third line has I have all positive values. Then I can see that the highest possible upper boundary would be 2. So I know that I want to look for numbers that are below 2. All right, if I want to try to test a lower boundary, I'm going to pick a value, a lower number. So let's say negative 1. Let's just test that. If I were to do my synthetic division for that, I'm going to quickly do that. All right, if the third row, I'm going to look at this row that's underneath here. And I'm going to look at, well, do the values alternate? So this first value is positive, then I have a negative, then a positive, then a negative, then a positive, then a negative. That certainly looks like it alternates. So that possible root is considered a lower boundary. So I know that if I were to have a rational root somewhere in there, it would need to be between negative 1 and 2. All right, so let's look at the example that says list the possibilities for rational roots. So it does not actually want us to find all the roots. It just wants us to find the possibilities. All right, so first thing I would do is I would get rid of this fractional coefficient. So I'm going to multiply by 3 to the whole equation. So I get 2x to the third minus 3x squared minus 15x plus 6 equals 0. So I'm going to look at what are all of my p's. Need all my factors of 6. That's 1, 2, 3, and 6. And all of my q's, which are all the factors of 2, which are 1 and 2. So I just need to write these out. So I know p's over q's can be any combination of positive or negative values with 1, 2, 3, or 6 in the numerator, and positive or negative values with 1 or 2 in the denominator. So I'm going to write that out. I could have plus or minus 1 over 1, 1 over 2, 2 over 1, 2 over 2. I could have 3 over 1, 3 over 2, 6 over 1, and 6 over 2. Now, some of these are repetitive, and we're going to reduce them to make them look better. So we got plus or minus 1, 1 half, 2, 2 over 2 is 1, so we got that already. 3, 3 halves, 6, and 6 over 2 is 3. Now I'm going to say it can be positive or negative, anything on that list, but you could also write a plus or minus next to each of those values. We have find the rational roots and solve the equation. So when it says solve the equation, that means find all the roots. It says use the rational roots theorem and the upper and lower bound theorem. All right, so first thing I want to notice is that it is a 4th degree polynomial. So at most, I will have 4 roots. I know I have to have 4 roots of some kind. They might be real, they might be imaginary, they might be rational, they might be irrational. All right, so we're going to try this out. So let's try first doing p's over q's. What are all my possible roots? So I need to look at what are all the factors of 24. All right, so this one has a lot of factors. So we have 1 times 24, we have 2 times 12, 3 times 8, 4 times 6. Any of those could be positive or negative. And then factors of my lead coefficient, which are 1. So I know that it's any of these numbers in the numerator over 1. So it could be plus or minus 1, 2, 3, 4, 6, 8, 12, or 24. And any of those could be positive or negative. All right, so now without a calculator, how would I go and decide, well, which of those numbers do I want to check? I know that they're not all going to work because there's 8 different numbers. They could be positive and negative. So really there's 16 choices to choose from. So I'm not going to do synthetic division 16 times. So let's just try one. All right, let's say I try 3. We'll talk later about how to narrow down a little bit instead of just blindly picking. All right, so I'm going to go do 3 times 1 is 3. 1 plus 3 is 4. 3 times 4 is 12. We had to get negative 13. I get negative 39. Get negative 40. Get negative 120. And I get negative 96. All right, so going back to the upper and lower bound theorem, well, I have to have the third line be all positives. That didn't happen. And the other option is to have positive, negative, and that didn't happen either. So this value of 3 is neither an upper boundary or a lower boundary. And I know that it certainly is not a root because this value is not 0. So it's not a root, but it's also not the upper boundary, and it's not the lower boundary. All right, so I'm going to see if I can find the upper boundary. I'm just going to pick another value. It's got to be on my list over here, so I'm going to choose 6, and I'm going to do my synthetic division again and see where we're at. So I get 6, 7, 42, 17, 102, 101, 606, and 630. All right, so what do we notice about these numbers? These are all positive numbers. So that tells me that this is my upper bound. So I know for sure I don't want to try anything else that's higher than 6, so don't worry about that, right? So now I'd like to maybe just see if I can find one that works, right? I know I got to pick a number that's lower than 6, and it's going to pick 1. So if I try 1, I've got 1, 1, negative 25, negative 1, and 24. And I'm going to do my synthetic division. And what do you know? I have a 0 as a remainder. So the remainder being 0 tells me that I have found one of my roots. My root is 1. Okay, so now I have found one of the 4 potential roots. I'm going to then do synthetic division again. I don't want to pick anything that's higher than 6, right? So I'm going to just try some negative numbers now. But this time I'm going to continue on this because right now we've got a cubic function, right? It's represented by these coefficients, 1x cubed plus 2x squared minus 23x minus 24. So now I really just need to continue on with this, not the original quartic function. So I'm going to try negative 1. So negative 23 there. And I'm going to see what happens when we do synthetic division. All right, so that tells me that that is also a root. So I have now found 2 roots. One of them is 1 and one of them is -1. And now I need to find the last 2 roots. So if I remember this is a quadratic, I know that the 1, 1, and -24 represent 1x squared plus 1x minus 24. All right, so I need to try to factor that, but that's not going to factor because there's nothing that multiplies to -24 that adds to 1. So instead, I'm going to use the quadratic formula. And if you don't remember that, it's the opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. All right, so that gives me -1 plus or minus the square root of 1 plus 96, which would give me the square root of 97 all over 2. Now, 97, you can't simplify the square root of 97, and you can't reduce anything. So now I have found my 4 solutions. There are 2 here, 1 here, and 1 here. And that gives me all of my roots because remember, it was a quartic function. I should find 4 solutions. All right, moving on to number 3. I would recommend that we do this one a different way. So first thing we're going to do is just find all the solutions. So I know that I'm going to look at p's and q's. So if I look at p's over q's, I want all the factors of -5, which are plus or minus 1 and 5. And I want all the factors of 4, which are 1, 2, and 4. So I know that for my list of possibilities, I could have plus or minus 1, 1/2, 1/4, 5, 5/2, and 5/4. All right, so I would suggest that we should graph this on the calculator and then find a root there. All right, so we're going to use our calculators to find the root instead of trying all the guessing and checking with the synthetic division and the upper bound, lower bound theorem. So we are going to graph. We're going to go to y equals, and you do 4x to the third. Make sure you hit the right arrow to get out of the exponent, plus x squared minus 20x minus 5. All right, so I'm going to hit graph, and I can see that, remember, I'm looking for potential rational roots at 1 or -1, 1/2 or -1/2, and so on my list. I can see that there are 3 roots. One of them looks like somewhere around -2. One of them looks like +2, but it's a little off. And then one of them looks like it's in between -1 and 0. So the easiest way to find out, is there a solution at -2, let's say, is, well, it's not on our list. So -2 isn't even possible. All right. +2 is also not on our list. So now I need to look in between 0 and -1. So I hit the trace button, and I'm going to type in what are some values that are in between -1 and 0. Well, -1/2, that works. Nope, actually it doesn't work because the y-coordinate is 4.75. It should be 0. So let's try -1/4. That's my only other possibility, so this one better be right. And it says y equals 0. That tells me that I should use -1/4 as my initial root. And then we're going to continue with synthetic division from there to find the remaining 2 roots. All right, so now that we have found the root on our calculator, we know that the root is equal to -1/4. So that means I'm going to do my synthetic division with -1/4. So I'm going to put down my coefficients here, and I'm going to do my synthetic division. If I do it all correctly, remember I should get a remainder of 0. So if I add -5 and 5, that gives me 0, which is great because now I know that I have a quadratic that is 4x squared plus 0x minus 20. All right, so I'm going to solve this using the square root method. So 4x squared minus 20 equals 0. If I add 20, I get 4x squared equals 20, x squared equals 5. And that tells me that x equals plus or minus square root of 5. All right, so since it is a cubic function, I should have 3 solutions. So I have plus root 5, negative root 5, and also negative 1/4. There are my 3 solutions. 1, 2, 3, and we're all done.